So this is the first major update for the BSX, my Z80 Homebrew computer. It's actually starting to look like a proper computer now. We have RAM as well as ROM. We've got output via this rather nifty LCD display here. We've got input and output via this board here, this microcontroller board. This is a Blue Pill STM32 microcontroller. It's effectively an Arduino on steroids, and it can be programmed using the Arduino IDE. I'll come on to that in a bit more detail later. As you can see, we've got all the major components: memory, input and output, and a CPU. So let's go through the changes in more detail now. First, the RAM. So it's not just a case of plunking the RAM on the board along with the ROM, wiring it into the address bus, and it will just work. We've got to do a little bit more work in order to make sure that when the Z80 requests data from an address or writes data to an address, it puts it or fetches it from the correct chip. The first 32K I wanted to be ROM, and the upper 32K I wanted to be RAM. So the easiest way to select that is by checking whether the topmost bit, A15 on the Z80 address line, is 1 or 0. If it's 0, then the memory address being referenced is less than 8000 hex or 32768, so it's in the bottom half of memory. So it should be fetching the data from the ROM. If bit A1 is set, then I should be fetching the data or writing the data to the RAM. Now, chips usually have an enable on, memory chips, and if this is pulled low, then the chip data lines are made available to the bus, and if it's pulled high, the chip becomes transparent to the bus. So what we want to do is set this chip select low if A15 is low or 0, and set this chip select to low if A15 is high or 1. And we achieve that using this logic chip here. It's a 74HCD139. It's a decoder chip, line decoder chip. It has 3 inputs, G, B and A, which are here, and 4 outputs, Y0 to Y3. In fact, it's got a pair of these, so you can see on the other side of the chip it's duplicated. So you've got 2G, 2A, 2B, Y0, 1 and 2, and 3. So we're only going to use this side of the chip, and we're not going to use all of the pins. The way I've wired it up is that the memory request I've wired into the G pin, so that's pin 1 on the chip. B, I've just pulled down to ground, so pin 3 has gone down to ground, and pin 2 is wired to A15. And I'm only using 2 of the outputs, Y0 and Y1. So this is the logic table for the chip. The way this works is, depending upon the state of these 3 inputs, you will get this output. So if, say for example, G is low, B is low, and A is low, then pin Y0 on the chip will be low, and all of the others will be high. So if you look at my truth table here, which I've modified to reflect what's going on, I've hidden all the stuff that's unnecessary. We're not using Y2 and Y3, and ground is never going to be high. You can see that if the memory request line is high, i.e. the Z80 isn't requesting memory, it doesn't really matter what these two are set to. Y0 and Y1 will both be high. Because the chip select is active when low, it means that neither of the chips, ROM or RAM, will be selected. However, if the memory request is low, these two rows come into play. So if A15 is low and there's a memory request, then Y0 is low and Y1 is high. So I need to connect Y0, which is this pin here, to the chip select of the ROM. You just about see it snaking around the back there to the ROM. Similarly, if A15 is high, then Y0 is high and Y1 is low, which means that the ROM will be deselected, but the RAM will be selected. So you can see here I've connected Y1 to the chip select of the RAM. This RAM chip's actually got two chip selects. There's one chip select which is active low, and there's another one here which is active when high. So all I've done is I've connected to the chip select which is active when low, and I pulled the active when high one high. The chip will only become active when this is pulled low. So that's how we address the RAM. How do we do the output then? Okay, well, there's two things going on with the output. The first is the LCD display, and the second is terminal output via putty. So this is connected to the PC not just for power over USB, but also data. Putty is a serial terminal package. It's commonly used for connecting to things like Telnet over the internet and FTP, but it can also connect to things using serial ports. Now, the STM32 appears as a serial port when connected to a PC. So from my setup, it's actually connected as COM port 2. So I've connected putty to COM port 2, and I can now communicate to the STM32. The STM32 just acts as a dumb terminal, so it passes all of the information sent to it over the serial port from the PC down to the Z80, and the Z80 responds by passing data back up to the STM32, which then sends it back to the PC over the serial port. So the STM32 is actually wired up as a device. So we've got the 8 data lines here. It's wired up to IO request, read and write on the Z80, plus it's also wired into the first 3 address pins, giving us a total of 8 addresses that we can use to address this, which might be overkill, but it'll come in handy later. And the LCD display is simply wired into the STM32. So the STM32 is responsible for all the I/O. I've written a small sketch on the Arduino which controls the input and output. So it masquerades as a device as far as the Z80 is concerned. So it puts data on the bus, and it also pulls data off the data bus, responding to the Z80 read and write requests. And I've put some diagnostic information in the sketch so that on the first 3 columns of the LCD we get the address that it's currently looking at between 0 and 7, all the I/O for keyboard and output to putties on port 0. That's whether the read line's active, low, and that's set when the write line's active or low. And the rest of the data is the serial data, which echoes that which is displayed on putty. So the sketch looks a little like this. Fairly standard Arduino sketch. So at the top I've defined some constants for the pins the devices are connected to. So these are the pins for the LCD, and these are the pins for the Z80 interface. So you can see I'm connecting IO request up, the read and write lines, so that determines whether the Z80 is fetching data or writing data to this sketch. The free address lines, so this effectively has got 8 registers, and the 8 data lines. We also set up a serial communications. When we initialize, we set most of the pins to input, with the exception of the LED, which we flash whenever or not there's a change on the IO lines. And this function here sets the data direction for the 8 data lines, data pins. We attach an interrupt to the IO request line. So when that goes low, it's falling, we run an interrupt. Because we only actually want to fetch data or write data when the IO request line goes low. There's in the main loop then, we check whether or not some data's come in from the interrupt. So every time the interrupt happens, this counter changes, IO count, and we've got a store of it in the previous count. So if it doesn't equal, if IO count doesn't equal previous count, then we know the interrupt's happened. And then we store the IO count in the previous count. So basically we're just detecting a change with these 2 lines of code. And then we deal with the register. So at the moment I've only actually got 1 register in, which is register 0, address line 0, 1 and 2 set to 0, and that's the serial IO. So I'll just scroll down to the interrupt handler. This is where the bulk of the work happens. So we read in the address lines A0 to A2 from the Z80. So that determines which register the Z80 is trying to look at on the in the sketch. We get the read and write lines. So that determines whether or not the Z80 is requesting data or writing data to this sketch. If there's an IO read, what we need to do is read the data from the Z80 data lines, because it's with respect to the STM32, not the Z80. So the Z80 is saying you need to read the data off the data lines at this point if the IO read line's set low. So we just combine all of the data pins using this function here, which shifts them in place and ORs them all together to form a byte, and then we store it in a buffer. This buffer has got a store for each of the IO registers, so it's an array that's defined up here somewhere. Let's have a look. There we go. So we've got a buffer for the data reads and a buffer for the data writes. Each one of these corresponds to one of the 8 registers. And then if we're writing data back to the Z80, we fetch data from the write buffer, which will have been put in the loop above. And then we very briefly set the data direction to output. Write the data to the pins, So we do basically the reverse of what we're doing up here, and then we set the data direction to input. The STM32 and Arduinos don't have bidirectional inputs. They're either output or input. So we're kind of faking bidirectional inputs here. By bidirectional, I mean you can read or write them. You don't necessarily need to set them to an output or an input state. And the rest of the code up here in the loop is to do with passing data from the serial port to the buffer and back again. So IO mode 0 is the function which handles the serial IO. So if we look at that function, if it's an IO write, then we try and read data over the serial port from PuTTY in this instance, or it could be any other package that dumps data over the serial port. And then we stick the data into the data buffer for write. IO register will be 0 at this point, so it will set it to the first entry of the array. And if there is no data, we just clear that down to 0. Otherwise, if we're reading, we get the data from the read buffer that are being put in via the interrupt routine. We write the data out over the serial port to the PC, and then there's a little bit of code in here which is to do with writing out output to the LCD. So there are 9 characters reserved on the bottom row of the LCD to the right, which echo the characters that are being output over the serial port. So this just maintains that buffer. Output it to the string. If the string length is greater than 9, then remove the leftmost character from the string. And that's it. It sounds a lot more complicated than it actually is. So there's some corresponding code on the Z80 which I'll briefly go through. So the Z80 code, which resides in ROM, there's a bit of preamble in order to get this working. So the Z80 will start at address 0 once it is powered up or reset. So I disable the interrupts and jump to the start function. I've not put anything in the restart instructions yet. The non-maskable interrupt isn't working at the moment because it's not wired up. But just in case it does happen, that does nothing. It just enables interrupts and rets. I've got a Mem Test which I'm skipping for the moment because it's incredibly slow. The processor's only running at a maximum of 3.5 kHz at the moment, so it takes about 10 minutes to complete the memory test. I have tested it once just to make sure that the RAMs are working, but for the moment, whilst I'm testing code, I'm skipping that. That will be enabled in the next version where I get the clock speeds up a bit. And then we print a nice startup message. So how do we print strings? So let's scroll down to print string. Just gone past it. We call print char, which I think is down here somewhere. Print char simply outputs the charts to port STMIO, which is defined up at the top as port 0. So when I say registers on the Arduino sketch, this directly corresponds to the ports that the Z80 will need to write to in order to write data to the STM32 Blue Pill. There's no decoding going on at the moment. It's only looking at the first 3 address lines. So I could write to port 0. I could also write to port 8 or port 16. In fact, it's only looking at the first 3 bits. So the ports duplicated every 8 addresses through the Z80 address space. That will be fixed at some point when I get more devices on there, like the video chip or the AUI chip, but for the moment it will suffice. And for input, we have an input loop. I just read from the port. So if I go back to the board, you can see the LED flashing. If I slow the board down, that is flashing every time there's an I/O request. So that directly corresponds to this loop here. You can see it's doing an NA to port 0. It's flashing the LED as a result. And you can also see here that the right line is active. That's because the Z80's trying to read data with respect to the device. So it means that the device is writing data back to the Z80. At the moment it's just writing zeros because there's nothing on the serial port. So if I invoke putty, if I do a reset now, there you go, you can see the data is being sent not only to putty over the serial port, but it's being echoed on the LCD. I slowed it down deliberately so you can see the message. If I clock the processor up to 3.5 kHz and press reset, you can see it's a lot quicker. So the Z80 code that I've got running over here is a basic monitor program. So there are a few functions in there. There's memory dump, there's memory load, and there's a jump function. These correspond to functions that I can type in now. So if I type M, I don't know, 0,50, it will dump out over the serial port the memory contents from address 0. It's all in hex. So I can dump out the contents of RAM. Let's go to 8000. Let's have the first 32 bytes of RAM. I've got a jump instruction in, so I can jump to any address. So I can jump to address 0, which should restart the ROM. Jumps back to ready. And there's also a load. Now, load is used in conjunction with a PowerShell program, which loads data into RAM over the serial port. So it'll open a file, write to the serial port a header which includes the letter L for load, a carriage return, and then 2 words. The first word being the address where I want the data to be loaded in RAM, and then the second word, the length of the data stream. And then the Z80 code if we look at fun memory load, you can see here I'm reading in the start address, and then I'm reading in the length of the data stream, and I'm just going in a loop then, reading the data from the I/O port and writing it into memory. So there we have it. It's a bit bare bones, but it is a computer. I can load data into RAM from a PC. It's got output and input and a very simple Z80 monitor program. Full details of this are available on my website, www.breakintoprogram.co.uk, and all of the hardware sketches, the Arduino sketches, and the software are available on my GitHub account. details on my website. I hope you've enjoyed the video. If you like what I'm doing, then please subscribe. Thank you very much for watching. Goodbye.